Okay, let's just dive right into this explainer, because today we are going to discover how to transform completely everyday kitchen items into a thrilling laboratory for scientific discovery. Seriously, if you've ever felt that intense, mounting pressure to come up with something fun, educational, and genuinely engaging for your family on a rainy afternoon, you are in the exact right place. We're going to look at some really fantastic source material today to help you build the ultimate at-home science curriculum.
Right, so it's the modern parenting struggle, isn't it? You get that inevitable chorus of, "I'm bored," and you have that constant nagging temptation to just hand over a tablet or turn on the television. We've all been there. But keeping kids entertained without screens, it doesn't actually have to be a battle. Proposing engaging hands-on science is honestly the ultimate cure for boredom. And the absolute best part about this, kids don't even realize they're learning when they're super busy making a giant mess and asking, "Wait, what happens if we do this?"
I really want to empower you right out of the gate here. You absolutely do not need fancy lab equipment, you don't need expensive mail-order kits, and you definitely don't need a degree in physics to make this happen. The true magic in our source material today is that everyday items, we're talking baking soda, dish soap, salt, eggs, these are literally the only tools you need to unlock the wonders of science. You're basically just taking things lying around the house, mixing them with a little bit of curiosity, and creating memories that will stick with your kids for years.
So, here is our game plan for today. We're going to start off with wild chemical reactions, move right into the rules of density, then we'll tackle physics and pressure, and finally we'll wrap up by exploring the true joy of discovery.
All right, let's kick things off with Section 1, Chemical Reactions. We are looking at the wild and the unexpected.
So the absolutely crucial point to understand here is how a catalyst works. Take hydrogen peroxide, right? H2O2. It is basically just water, H2O, but it's got this extra oxygen atom tagged on. Now, a catalyst is a substance that speeds up a chemical reaction without actually being consumed by it. In our very first experiment, using something as unbelievably simple as dry yeast mixed with warm water acts as the perfect catalyst. It's going to rapidly tear that extra oxygen atom right off the hydrogen peroxide molecules.
And that leads us straight to the famous elephant toothpaste experiment. Here's your at-home recipe. You take 6 ounces of hydrogen peroxide, a tablespoon of dish soap, a squirt of your favorite food coloring, and you mix that with 3 tablespoons of warm water and a tablespoon of dry yeast. When you combine them, oh man, the yeast pulls the oxygen off the peroxide, the dish soap catches that escaping oxygen gas, and it creates this massive, beautiful, foamy eruption. It brilliantly illustrates what we call an exothermic reaction, which just means it actually gives off heat as it foams up. It'll feel warm to the touch. Just remember, adult supervision is always recommended for this stuff.
Now, you might have actually seen former NASA engineer Mark Rober do this on a completely massive scale online. Let's compare the two real quick. The at-home version we just talked about uses standard 3% hydrogen peroxide and yeast. It produces a really smooth, safe, laminar flow of foam. The television version, however, that uses a highly concentrated 30% hydrogen peroxide and a chemical called potassium iodide. And that creates an explosive, incredibly hot, and frankly dangerous reaction that really should only be handled by professionals in a lab setting. So yeah, definitely stick to the 3% for the kitchen.
Let's pivot to a totally different but equally fascinating concept, surface tension. I want you to picture the top layer of water molecules almost like they're joining arms and holding on super tight to form this sort of invisible skin. If you sprinkle some pepper on top of a glass of water, it just floats there, right on that skin. But if you introduce a surfactant, like just a single drop of dish soap, it immediately breaks those molecular bonds. It rips the surface tension apart and causes all that pepper to instantly dart out to the edges of the plate.
You can actually take this surfactant science to the next level with something called the magic milk experiment. First, you pour full-fat milk into a shallow dish, and it really does have to be full fat. I'll explain why in just a second. Add a few drops of food coloring around the center, then just gently touch the surface with a cotton swab that you've dipped in dish soap. As the dish soap breaks the surface tension, its molecules frantically search for the fat molecules in the milk to bond with. This invisible microscopic chase basically pushes all the food coloring around, creating this swirling, moving rainbow. It's incredible. If you try this with skim milk, well, there just isn't enough fat for the soap to chase, and the reaction is pretty boring.
Okay, moving right along to Section 2. We're going to look at the rules of density. Why do things float or sink?
So, density is simply a measure of mass per unit volume. Think of it as how much stuff is packed into a specific space.
The golden rule to remember here, the magic number, is that regular tap water has a density of exactly 1 gram per milliliter. Objects are going to float if their density is less than 1, and they are going to sink straight to the bottom if their density is greater than 1. This is the foundational rule for our next set of experiments.
Check out the floating egg trick. An average raw egg has a density of about 1.03 grams per milliliter. Because 1.03 is just slightly greater than water's 1.0, when you drop an egg into a regular glass of tap water, plop, it sinks right to the bottom. But here's the science magic. If you stir about 3 tablespoons of salt into that water, you are actively packing more mass into the exact same volume of liquid. You literally increase the water's density so much that it is now heavier than the egg itself, and the egg magically floats right up to the top. How cool is that?
You can visualize this whole density concept brilliantly with a rainbow in a jar. By pouring different liquids into a tall glass in a very specific order, going from heaviest to lightest, they will actually stack right on top of each other without mixing. You start with super dense honey at the very bottom. Then you carefully layer in dish soap, some colored water, vegetable oil, and finally some rubbing alcohol right on top. You end up creating this beautiful, interactive visual lesson in liquid density that honestly looks like a modern art piece just sitting right there in your kitchen.
All right, let's jump into Section 3, Physics and Pressure, where we uncover some of the invisible forces around us.
Using incredibly simple setups, like literally just placing a funnel into an empty plastic water bottle, you can observe some surprisingly complex fluid dynamics. For example, if you fill that bottle with water, add a single drop of dish soap and a little pinch of glitter, tighten the cap, and swirl it really rapidly in a circle, you'll actually generate a vortex. The physics of that swirling water creates a localized area of low pressure right in the center, forming a perfect, mesmerizing water bottle tornado right there in your hands.
Or you could try making dancing raisins and corn. Just fill a tall glass with seltzer water and drop in a handful of popcorn kernels. Now at first they're going to sink, but then the carbon dioxide bubbles from the seltzer begin to nucleate, which just means they attach themselves to the rough surface of the kernels. As Mark Rober so perfectly described it, these bubbles act like tiny little arm floaties that lift the heavy kernels all the way up to the surface. Once they get there, the bubbles pop in the air, the floaties are gone, and the kernels sinks back down to do it all over again. It is basically a completely natural lava lamp.
And of course, we absolutely cannot talk about pressure without bringing up the classic egg-in-a-bottle experiment. If you have a hard-boiled, peeled egg and a glass bottle with a neck that is just slightly smaller than the egg, you simply cannot push it in without making a huge mess. It just won't fit. But if you drop a small piece of lit paper inside the bottle and quickly place the egg on top, science takes over. The heated air molecules inside stretch out and escape past the egg. But as soon as the flame uses up all the oxygen and dies, that remaining air cools down and rapidly shrinks. This sudden contraction creates a massive drop in pressure, a literal vacuum, that violently sucks the egg right into the bottle with this incredibly loud pop. It is so satisfying. Finally, let's wrap things up with Section 4, the joy of discovery. Because really, it's all about asking why. You see, the entire core of the scientific method is essentially just a game of changing variables to see what happens. When you do these experiments with your kids, don't just do them once and walk away. Change one thing at a time. Tweak it. For example, when you're testing the dancing corn, try using a much taller glass cylinder to see if the kernels can actually make it all the way from the bottom to the top. Try warm water versus cold water in your elephant toothpaste. By changing just one single variable, you learn exactly what is driving the results. And this really brilliantly illustrates the whole point of doing this, perfectly summed up by a fantastic quote from Mark Rober. The most important words in science aren't eureka, it's that's interesting. The true magic of at-home science isn't just about making a really cool, foamy mess on the dining room table. It's about paying attention to an unexpected result, tilting your head and asking, wait a minute, why did that happen? Because that right there, that is where true curiosity is born. So I leave you with this. What variable are you going to test first? Grab some baking soda, maybe some dish soap, and just let your curiosity guide you today. Because if you can teach a kid to look at a mess on a kitchen table and ask why, you aren't just entertaining them for a rainy afternoon, you are literally teaching them how to question the entire universe. Thanks so much for joining me on this explainer, and hey, happy experimenting out there!